Hello everyone. With this video, we are going to start the final module of our course, and this module would be on the physical layer of the database. So, if you recall this diagram from our earlier lectures, I said that in any database system, you have conceptual model, a logical model, and a physical model. And if you pick any modern day database systems like Postgres or Oracle and so on, they mostly focus on this part and they leave the conceptual modeling part to the end users, right? uh, Now in this course, we covered different things. Like at conceptual model, we discussed how to draw ER diagrams, how to model real world concepts in the application, and how to create tables and all that, right? So in the logical model, we studied relational operators, SQL query language, and all that, right? And finally, in this with this video and the following videos, we are going to talk about uh, how to implement the logical model at the physical layer. So that means, when you're writing an select query, select star from employee where a certain where clause, right? So we are writing this in pretty much English language, right? But how to actually implement that at the back end, that is what we are going to study in our physical model, right? So this physical model is more or less broken into four parts. Of course, it's a very wide topic and also an active area of research. But what I'm going to do is that I'm going to give you an high level view of certain things, so that we cover more breadth than the depth. So so over here, I'm going to cover something called as file structures. So that means, whenever you have a large file, how to store that file in your database, right? Especially when the case where your file is growing or shrinking with size, right? So that part is called as file structures. And after this, in the next set of videos, we are going to cover indexing structures for database system, right? So whenever you have an select query, let's say that select star from employee where employee dot salary is greater than 1000, right? So something like that. So wherever you have some kind of a where clause, you usually use some kind of an index structure to search through your file and return the answers quickly, right? So we're going to cover something called as a B plus tree, which is a very widely used and very popular indexing structure at the databases. So we are going to cover that in the indexing structures module. And the last two one would be on query optimization and transaction processing. So given that this is just an introductory course, I'll not be able to cover these things in great detail, but nevertheless, I'll give you the overall idea on what kind of things that database needs to typically care about when it is trying to build systems which scale to large uh, data sizes, right? So if you pick any real world database system which is deployed, uh, the size is usually in terabytes, not less than that, right? So when you are handling queries and data of such large scale, then you got to be smart about things. Otherwise, your system can slow down significantly. Okay, so let's go forward. Okay, first I'm going to cover some basics of disk storage. It may look little boring to you, but what I'll do is that I'll cover the interesting parts, and the remaining things, they are just basic definitions and all that. They're still important, but I think you can read them from the textbook also. No big deal. Okay, so first we'll talk about basics on disk storage, right? So I think given that you all are, I think, doing operating systems on the side, you know these things, right? So a computer has something called as a primary storage and something called as a secondary storage. In the primary storage, you have things like main memory and CPU cache, right? So they are very fast, but they are very expensive, and moreover, they are volatile in nature, right? But for databases, you need something uh, that can persist across system reboots and all that. So for that, we have secondary storage, and certainly secondary storage options are not so fast, and but the added advantage is that they are not volatile in nature, right? So the most typical ones being magnetic disks, right, which are widely used in the CPUs. And nowadays, increasingly, we are getting this flash memory disks also, right? Uh, so the deal with the flash memory is that it is also non-volatile, and certainly faster than magnetic disks. But there are sort of two disadvantages here. So one is that flash memory, it's a bit expensive. So even when you are purchasing your laptops and all that, you see that if you opt for something called as SSD, that is the flash memory hard drive, that is usually more expensive than your typical HDD, which is your magnetic disk drive. Okay, so the flash memory, it is fast, but it is expensive. So when you are planning for storage at the scale of terabytes or petabytes, having everything on a flash memory can dramatically increase the cost of your infrastructure investment, right? So even though flash memory is the new technology, but sometimes the cost plays some interesting tricks. Okay. And one more thing which must be noted with flash memory is that it can have only finite number of erasers before it goes down, right? So that is another disadvantage. Okay. So the summary statement to remember is that both your HDD, which is your traditional magnetic disk, and your SSD, which is the newly emerging flash memory based storage, they both have their own advantages. SSD is fast but can have only finite number of writes, and moreover SSD is expensive. HDD is little slow, but but it's cheap. So if you are planning for storage of petabytes, then HDD certainly is in the game. Okay, so let's try to uh, yeah. So okay, I think I can skip this. So just an sort of a motivation slide on why do we need to be smart about storing databases, right? So as I said, databases are typically large in size, in terabytes. Any realistic real world database system will go into terabytes. So even if your operations, if your system is just 1 second or 2 seconds slow in terms of query performance, so then that slow inefficiency, when you sum it up across lakhs and or maybe millions of transactions, the overall throughput of the system goes down very much, right? So that is why we have to be extremely greedy, in the sense that we have to have a system where the query performance, insert, delete, and select queries, they are as efficient as possible. Okay. Okay, so now getting into the details of a magnetic disk. So a magnetic disk, it has several surfaces, and on each surface you have something called as tracks, and tracks are divided into sectors, right? So sectors is pretty much hard coded on a disk surface, right? Let me just go to the image. Yeah, so so this is a surface, and then you have a track and each track is sort of, you know, divided into sectors. Okay. Now, when you put when you look at a magnetic disk, then it has several surfaces, right? Several tracks. Sorry, several surfaces, and each surface has several tracks, and they are sort of stacked together on one on top of the other, on a spindle, right? So this whole system of surfaces, it rotates, and then there is an read write arm, and that read write arm sort of goes in and out to read different tracks. So that means, so let's say that this is the current position of your read write arm, and you have an hardware address which comes in, right? So first you have to obviously figure out which of your surface contains that hardware address, and that hardware address is basically a combination of your you know it's a combination of your the surface and what track you are on, and then finally the sector, right? And based on that address, this read write arm, it will move forward to place the head on the corresponding track, right? And then once it is on the correct track, then your spindle sort of rotates to make sure that the disk block that you want to read or write comes under the disk head. Okay, and once it is under the disk head, you read the corresponding sector. Okay, let's step further. Okay, so now there is an operating system concept. I think you must have studied in your OS class also. There is something called as disk pages, right? And some people call it disk blocks. There might be a slight difference between these two words in the sense that one might be more used in the OS literature and the other one may be more in the hardware literature. In this course, we will assume that one disk page is equal to one disk block, although in theory they may have slight differences. And the key thing to note is that one disk block or one disk page, the way I'm going to use in this course, I'm going to use these terms interchangeably. The size of these things, they are set during the operating system, right? So one disk block can be a couple of sectors, so that depends on the hardware capacity of your magnetic disk drive. You can assume that one disk block is maybe couple of sectors. Okay. Yeah, and the thing to note is that from the hard drive you always read or write in the form of one disk block. The simplest thing that you can assume is that one disk block is one sector. It cannot go less than that. It's hardware wise also, it is not possible to address anything which is less than one sector in size. Okay, so the lowest value that a disk block or a disk page can take is one sector, but depending on your hardware capacities, it can be maybe few sectors. Okay, so we'll take that with a pinch of salt, right? So your magnetic disk that you have, it is an random access machine. So that means you can access addresses in random order with no constraints, and you will still be able to get the data that you are interested in, right? And as I said before, the transfer between main memory and your disk always takes place in the units of disk blocks, right? Okay, so your hardware address, as I said, it's a combination of cylinder number, track, and sector within the track, right? So you may recall that earlier I said disk surface and then track, right? So these are not completely different. So let me take a minute over here and then explain. Okay, so here in the slides I'm saying that your hardware address is a combination of cylinder number, track number and sector number. So let's go back to our figure and then see what it means. Okay, so first thing to note is that uh, so if you see a particular track, right? So you see this guy on disk 1 and this guy on disk 2, right? So they are sort of the same track, which are you know uh, which are stacked on one top of each other, right? So if you view this logically, all these tracks, you know, they sort of form a cylinder, right? So when I say the address contains a cylinder number, that means I am referring to this particular position, right? So your entire system of your magnetic disk, it will contain several concentric cylinders, and each cylinder is a collection of tracks, right? Because if, let's say, in this particular case you have 5 disks, right? So each cylinder is a combination of the tracks from these 5 disks, right? So depending on how you are fixing the addresses, I think the way this particular textbook is talking about is that first you define the cylinder number, means which of the cylinder we are interested in, and then in that particular cylinder you decide what is the track number, or uh, what is the surface number that you want to read, right? So there is a bit of an terminology change with the textbook did. Nothing to get scared about. So let me repeat one more time. So these circles, which this guy calls as track, when it comes to addressing, right? We are talking in the terms of cylinder, right? So a cylinder is a collection of tracks on the surface, the same track number, which is at the fixed radius from your center point. So after you get the cylinder number, you refer to the disk surface on which you are interested in. And that disk surface, I think, your textbook is calling it as track. So they're using the word in two different senses. Okay. And then finally, within that, once you have the appropriate track, you get the sector that you want to read. Okay. Okay, so what I did is, I changed this slide. While uploading, I'll put the updated slides. Okay, good. Okay, so now when you have to access the magnetic disk, this is sort of the actions which your computer does, right? So given a random hardware address, the first thing that we will do is that, the read-write head will move to the correct track or cylinder number, right? And I hope you now understand, right? So this is called as the seek time, and usually this is the this takes the maximum amount of time, right? Now once your read write head is in the correct cylinder number slash track number, then your disk starts to rotate under your disk head, such that the sector that you want to read comes under your read write head, right? So the time required for this rotation is called as rotational delay or latency. Of course, uh, the seek time depends on how much it had to move. So let's say it was originally at cylinder 0 and it had to go to cylinder maybe 10,000, and will take more time. That's okay. uh, and similarly, this rotational latency, uh, right? Suppose it was very close to the sector that it had to read, so it will take less time. If it had to rotate more, it will take more time, right? But those things, we take it with a pinch of salt. But despite all of these things, we'll say that the scientists and the research work in this area declared that seek time takes the maximum amount of time, right? Okay, so once the track is in its correct place, and the head is in its correct place, and then your spindle has moved to make sure that the sector that you want to read is under the read write head, then you actually go ahead and read an one disk block amount of data. So this is called as the block transfer time. So the total time to read an hardware address is seek time plus rotational delay plus block transfer time. And as said before, the seek time is usually much larger than these things. Okay. So I think I took some numbers from your one of the textbooks just to show how these things are. uh, for an example, so let's say that we assume the following parameters. So that means let's say that one sector has 4096 bytes, and let's assume that on an average we have 128 sectors per track. Of course, tracks which are closer to your spindle will have maybe less sectors, and the farther ones will have more sectors, but let's assume that we are doing some approximation here. And let's assume that we have some 16,000 tracks in my disk, right? And the disk speed of rotation is 7200 rpm. So therefore time for one rotation is approximately 8.33 milliseconds, right? And the seek time is defined as follows. So we'll assume that it takes 1 millisecond to start and stop, because there is a bit of an inertia which is involved when to start a stationary read write head, and to stop a moving read write head, you'll have inertia, right? So this is basically physics 101. And then so that is the 1 millisecond to start and stop, and then you have 1 millisecond to travel every 1,000 cylinders, let's say, right? So using that, let's try to calculate some numbers of disk access time, right? Okay. So the question that we are interested in is, what is the minimum and maximum time to read an 16384 byte disk block? Okay. So now let's try to derive some numbers and then see what is the minimum and what is the maximum time that my hardware disk uh, will take to read an 16,384 byte block. Of course, there are a bit of assumptions in this calculation, but hopefully it will give you an idea on where things lie. Okay, so the best case is when the disk head is just over the starting sector of the block that you want to read. So that means there is absolutely zero seek operation, right? In other words, this operation which I said, that your disk head moves back and forth to position itself on the correct cylinder or track, whatever you want to call, uh, that thing is not there. That is the best case. So that means so the disk seek operation is zero. And there is one more case. The second one being that this spindle, when it had to move to put the first sector of your disk block under the read write head. Let's say that you were so lucky that even the rotational latency was not required, right? So in the best case, you have no seek time, and you have no rotational latency. Everything is positioned just perfect, so that you just have to read that 16,000 byte block, right? So let's see how much that takes. So we assume that we have 4096 bytes per sector. So therefore, one disk block will span across 4 sectors, and that means your read write head must pass through 4 sectors and 3 gaps, right? So let's make some assumptions. We assume that each track is around 128 sectors and 128 gaps, because they all are laid around a circle. And let's also assume that area wise your gaps are 90%, and then sectors are sorry, gaps are 10% and sectors are 90%, right? So under these assumptions, if we have to read 4 sectors and 3 gaps, so the total degrees that that we have to read is 10.97. So so that arc of 4 sectors and three gaps will subtend an angle of 10.97 degrees on the center, right? So therefore, now if we have to read this much of arc on that, then what we do is that we have to multiply it by the time to rotate, right? uh, so if my time for one rotation is 8.33 milliseconds, then in 8.33 milliseconds I'm going to rotate for 360 degrees. So if I had to rotate just 10.97 degrees, how much time would I need to uh, spend in doing that rotation part, right? So that time comes out to be 0.00022.253 seconds, and then uh, time to actually read the sectors. Okay, of course, there is a bit of an assumption over here that so this 8.33 seconds which I told is the time required for one continuous motion, one continuous spin, right? But if your disk head is reading one sector at a time, it moves and then stops, it moves and then stops, so there is a bit of an inertia also. Okay, but those things are sort of ignored in this calculation, and this is typical of database world, right? Instead of getting the perfect numbers, database people try to get uh, in that right ballpark to make decisions. Okay, so the total transfer time, the best case transfer time for reading or writing an 16,000 byte block is approximately this much, right? So 0.000253 seconds, so that is the amount of time in that disk rotation, and whatever time you require to actually read the sector once it is under the head. Okay, and what is the maximum time? So in the maximum time, or in the worst case, what may happen is that you have to move your disk head across the entire disk. So that means your disk head was in the last cylinder, and then you had to read from the first cylinder, right? So it had to move the entire disk, and also you may have to do pretty much a full rotation, right? uh, so the key thing to note is that between the minimum time and the maximum time, so this part is the one which is sort of dominating the equation, right? So time to actually read the sectors is same across both minimum and maximum part, right? So that is the key thing to worry about. And if you want, you can put these numbers to see that this number, time to move the head across the entire disk plus time to do the one full rotation, this is going to dominate dramatically over this time to reading of disk blocks, right? So that is the summary statement that you should remember, right? You can plug in your textbook has an does this in detail. Ullman's textbook does this in detail, not the other one. If you want, you can take a look at that, right? Okay. Okay. So given that seek time is usually the greatest when it comes to reading or writing an hardware address, so there have been techniques to reduce that. So of course there are several techniques. The one which I'm going to focus in this lecture is the elevator algorithm. Okay, so let's see what is that. Okay, so elevator algorithm is an disk scheduling algorithm, right? From the name itself, you can guess that you know uh, the process of this algorithm is very similar to an elevator, which is making sweeps between ground floor and the top floor of a building, right? So the way we do is that, the disk head, it keeps making sweep from the ground, from the first track to the last track, and then again back and forth. It keeps making sweeps. And then what it does is that, as it is sweeping over a cylinder, it will check if there are any requests which are which correspond to that particular cylinder. If there are any requests, let's say that, it is going from cylinder 0 to cylinder 10,000, right? As it is going towards the higher cylinder number, it will check. Let's say it is passing over cylinder 5,000, right? So at that stage, it will check if there are any requests for that particular cylinder or not. If there are, then, it will make a stop at that particular cylinder, and then perform either read or write whatever was required, and then proceed in the same direction. Okay, and once it hits the cylinder number 10,000, it starts the reverse part. Okay, so now let's take an example for the elevator algorithm. But before we go into the details of the example, some parameters to note here. So the first one being time for transferring one disk block. Note that this is one disk block and not one sector, right? Because as I said earlier, depending on how things are between OS and your hard drive, one disk block can span across a few consecutive sectors. Putting all of them together, I'm saying that time for transferring one disk block is 0.25 milliseconds, right? But note that, this time does not include the latency and seek time, right? So those parameters are different. So when I say time for transferring one disk block, I mean that once your disk head is in the exact position that it needs to be, time required for reading one disk block is 0.25 milliseconds. So that's what I'm saying. Okay, and then after that we have average rotational latency. Remember, I said that, rotational latency is the time required for the disk spindle to rotate such that, the appropriate sector number is under the disk head. In worst case, it may have to rotate pretty much 360 degrees, but in best case it might be 0, right? So therefore, average rotational latency, on an average, we are thinking that it may have to rotate about 180 degrees, and for that we are assuming that it will take 4.17 milliseconds, right? And the seek time, as I said before, seek time is the time required for the disk head to move from one cylinder to another. Okay, as I said before, it is 1 millisecond to start and stop, and then 1 millisecond to travel every 1,000 cylinders. Let's say these are the parameters. Now on these parameters, let's try to work out an example, right? So let's say that you have these cylinder requests which are sort of queuing in, right? So this is a queue. That means that, first this cylinder request came, then this came, then this came, then this came, and so on, right? And then as and when the cylinder requests come, they keep adding, right? So one thing to note is that, I'm talking in terms of cylinder request only, because as I said, we will try to measure the seek time, right? So the actual hardware address, as you remember, it contains cylinder request plus some sector information also. But given that seek time is usually the dominating part in this example, therefore we are going to work with cylinder number only for just for the purpose of illustration. So that means, in this example, I have the following hardware address requests, and those hardware addresses are on these particular cylinders, right? So this one came first, then this one, then this one, then after maybe 10 units of time, then this one came, then this one came, and so on, right? So this is the time of arrival. Now we are going to compute the time at which they will be serviced, right? So let's say that we are the disk head currently at t equal to 0 was at cylinder number 2000. So how much time will it take? Pretty straightforward. No seek, I will require 0.25 milliseconds of time to actually read one disk block of information. And then I'm assuming that on an average, I will rotate maybe half the disk, right? So, so by the time I finish this particular, by the time I finish servicing this particular cylinder, this particular request, which is at cylinder 2000, I would have spent this much time, right? And then let's say that I'm assuming that the disk head is going towards the bigger cylinder number, right? So after finishing this, I'll go to cylinder number 6000 without any stops in the middle, because that's the queue, right? So the time at which this guy will get this address will get serviced is that this 4.12 seconds, this is coming from here, and after that my read write head has to move from cylinder number 2000 to cylinder number 6000. Okay, so for that how many cylinders I have to pass? I said 6000 minus 2000 divided by 1000. So this is the amount of time that I am going to require for passing over 4000 cylinders, right? So I said 1 millisecond per 1000 cylinders, so therefore for 4000 cylinders I will require 4 milliseconds. And I said that one extra millisecond over here is because of the initial inertia of start and stop, right? So therefore the total seek time for moving from cylinder 2000 to cylinder number 6000 for addressing this service is this part. This part is the total seek time. So one is for starting and stopping, the initial inertia part, and 4 milliseconds is for traveling, the actual travel of 4000 cylinders, right? Okay, so 4.42 milliseconds have passed. The next address to service is 6000. Seek time is this much. So after this seek time, you are on the correct cylinder. Now, once you are on the correct cylinder, as I said that some rotational latency will be there, which is the time required to rotate the spindle such that the sector that you want to read is under your disk head. So that is that rotational latency, as I said in our example, that we'll assume that it is usually half the disk, so 4.17. So that is why this 4.17 comes, right? So this is the rotational latency. And then finally, once everything is in place, I said that I would require 0.25 milliseconds to actually go ahead and read that, right? So that means by the time the cylinders, the address at this cylinder 6000 is serviced, my time has moved to 14.09, right? So you also check this calculation. If there are any errors, let me know, right? Okay, so now the time is 14.09. So in your queue, others have already uh, you know uh, gotten in. So therefore you see that there is, and you are moving in the direction of 2000 to 6000, and by the time this is finished, you see that this address is already there. But nevertheless, the thing to note is that there is an address request at cylinder number 14,000. So what will happen is that your disk head, it will continue moving in that direction. Okay, so it will continue moving in that direction, and after the 6000, it will actually process 14,000. 4000 is skipped, even though it has now come in the queue. So by the time the 14,000 gets serviced, how much is the time required? So time right now, current time is 14.09. It's the current time. Plus you have to move about how many cylinders? You have to move about 8,000 cylinders plus 1 millisecond for initial inertia. So 9 becomes your seek time, and this is the rotational latency and time required to read. So that part remains the same. So by the time this 14,000 address at the cylinder is serviced, the time has moved to this number, 27.76, right? So at this stage, again, I look in the queue to see if I have to go forward. So in this case, the 16,000 has already come by the time you finish servicing this, right? So therefore, I will go ahead and process the 16,000 request and then return back. The key thing to note here is that, if this 16,000 guy uh, was not in the queue already by the time this 14,000 was already serviced, if the 16,000 guy was not in the queues, for example, the 16,000 guy came at time 30, right? So by the time I finish this 14,000 cylinder, the time is only 27, right? So, at that stage, it may depend on the implementation, and what may happen is that, the disk head, instead of going all the way up to the 16,000th cylinder, which is the last one, it may decide to return back because there are no requests in the queue. And that will be the case if this guy comes at a very later stage. But in this example, it so happens that, by the time I service this address request on 14,000 cylinder, the last guy had already gotten it. So therefore, it will go all the way up to 16,000 and service it. So the order of processing these requests is first 2,000, then 6,000, then 14,000, then all the way up to 16,000. And this is only because the 16,000 guy came in by the time I finished processing this 14,000. Right? That is the only reason I will go to 16,000. We can make that assumption in this class. And after that, it will return back, right? So very similar to your elevator. It started at the ground floor, and then as long as it is seeing and request in the queue for higher cylinder numbers, it will keep on going forward. And at the point where it no longer sees uh, address requests at the higher cylinder number, or it has actually reached the top floor, it will start descending down. So that is the disk scheduling under elevator algorithm. Okay. So I did this calculation. You can cross check and you let me know, right? So you can compare it with first come first serve to see, what is the time of service request on first come first serve. So you may if you do first come first serve, then what may happen is that first you will process these three because they came at the earliest. Then again you will go back to 4,000. Then again you will go forward to 16,000 and so on, right? So that back and forth action will happen when it comes to first come first serve, right? So therefore disk scheduling via elevator algorithm is quite popular, right? And there's a well-known fact over here that if you have very few requests in your system, then first come first serve may perform okay. But as your pool of requests go very large, then elevator algorithm will start to give much better answers, right? And the primary reason being that in the elevator algorithm, it avoids that zigzag moment at fine level, which your FCFS, first come first serve will algorithm will do, right? Okay, so I think that's enough about elevator algorithm.